Hello, my name is John Bozard, and this is my Physics 2211 Lab 5, the falling slinky. The purpose of this experiment is to observe the motion of a stretched slinky dropped from static equilibrium and create predicted and experimental models that allow for data analyzation. I will also use fundamental physics principles to model and estimate the slinky's y position over time. On the right, you can see a simplified example of the thought process behind this lab. Once the hand in the picture drops the slinky, the bottom will remain in the same position as the top slowly drops. From this information, I concluded that the only forces acting on the spring in the green period are tension and gravity, which are equal in magnitude and are acting in opposite directions. Once the slinky drops below the red line, only forces of drag and gravity are present. In this lab, the momentum principle, F net equals delta P over delta T, is used to derive the velocity and position update formulas. Knowledge that the force of gravity equals mass times g, or the acceleration due to gravity on Earth, times direction vector j hat is necessary. In addition, the assumption that the slinky is initially at rest implies static equilibrium in which the magnitude of the force of tension is equal to that of Fg. Finally, it is important to note that the force of drag equals b times the magnitude of velocity times j hat, where b is the coefficient of drag. The mass of an original slinky is 6.1 ounces, or about 0.173 kilograms. I found its stretched length of 1.22 meters by estimating its height when compared to the man in the video provided through Canvas. The slinky is dropped from rest, and Tracker determined its initial position to be 0.003, negative 1.218, 0 meters. On the right is the y position versus time graph produced by Tracker. Let's analyze that now. Here's the full Tracker video. The origin is placed at the point where the slinky is dropped, and the calibration stick defines a reference length. As the video runs, you can see that the point mass analyzing the bottom of the slinky does not change until the top of the slinky pushes down. This change in y position can be seen in the graph in the top right and in the last slide. The position and time data points will be graphed and compared to those produced later on in the GlowScript code. For my GlowScript code, I tried to combine aspects from previous labs. In the leftmost box is the slinky's mass, initial position, initial velocity, acceleration due to gravity, the direction vector j hat, and the drag coefficient b. The latter was found by trial and error to achieve the correct scale. In the middle box, you can see a while loop for t is less than 5.55 seconds, aka the time before the bottom of the slinky moves. In addition, the net force and the forces of gravity and tension are defined. The velocity and position update formulas, as well as the code for plotting and outputting data, are present in both the middle and right GlowScript segments. The second while loop is defined from the time the bottom of the slinky moves to the time it hits the ground. The force of drag is then coded, and the net force in red is updated. My full code will be in the description, although once run, you will see some weird velocity and force graphs that show oscillation due to the small scale values, so just focus on the y position model. After I collected the data for the observed tracker and predicted GlowScript models, I graphed them together in Excel. Besides a few mild discrepancies in the points, most likely due to inconsistent point mass clicks or an unaccounted for force, the two y position versus time plots are very similar. Based on the graph, it is evident that the bottom of the slinky remained at a constant position with a net force of 0 until it was pushed down by the part above. The y position then began to decrease as the force of gravity overcame that of drag. Thank you.